All right, so this talk is going to cover basically the work that I did in French Polynesia from about 2014 to about 2018. And then I'm going to kind of give you a bit of an idea of what I wanted to present in a bit more detail in this talk, but I haven't quite had the time to complete the research because we're still kind of in the marking period of exams here. So the shot that you have in front of you, this is actually where I did my PhD. So this is One Tree Reef in the Southern Great Barrier Reef, right near Heron Island. And so a lot of the work that we ended up applying to French Polynesia was based off the initial work I did on this reef here, looking at these waves transforming and breaking on the reef and building all of the features that you see on the reef here. And more or less took that understanding and started working in Germany in French Polynesia, which is a bit of a weird thing to do. So a bit of an introduction to some of the concepts, and I guess there are people who are experts here in ecosystem services, so I'm not going to try and, I'm sure that that expertise is something that you are all more aware of than myself, but the coastal protection service provided by coral reefs is the great barriers to our coastline protecting these tropical systems. It's a really critical ecosystem service provided by coral reefs. It's probably comparatively understudied compared to other aspects of coral reef science. Yep. But one of the things that's kind of an unknown is how the impact of climate change will change the provision of this coastal protection service, both through the rising of sea levels, but also through the degradation that we've observed of coral reefs worldwide. And this work that I did was kind of trying to investigate how those two twin threats of degraded reefs and an increase in sea level would change the wave conditions over the top of coral reefs, similar to what you see over here on the left. It's one of the biggest unknowns, along with kind of the production of sediment, which is probably something that is I've found is less interesting to people when I start talking about sand, but it is crucially important because it's what builds all the islands and all the low-lying regions that are quite exposed to sea level rise. And there's very little data when I started doing this of people actually going into the surf zones of coral reefs in these regions over here on the left. And
hey Daniel, sorry to cut you off, mate. You're transitioning through the slides, are you? Well, we've just still got you on the slideshow, sort of not opening in presentation mode. Sorry to cut you off there.
Okay, so let me have a look. I'll just share straight onto PowerPoint then.
All right, sweet. Yeah, might be the way. Sorry about that, mate. We'll might have to switch gears when we go. Yeah, that's the one. Yeah.
That's a little bit better. Okay. Thanks, Sean. So all the points make sense. There's just some dot points here now that you can follow. Apologies, everybody. We're all learning here. So those are the points I've already covered. So I'll just keep going through. So this talk, the following things I'm going to go through is some of the stuff we did to try and provide insights into how the wave conditions would change on coral reefs and what this might mean for our low-lying coastlines and tropical regions. The idea is eventually this is something you can transition to places in Australia as well, which there's some preliminary work on that at the moment as well. Okay, so the regions I'm talking about and the reason why this is important, these are the kind of environments that we're talking about here. So Kiribati, which is on the left here, it's kind of one of the most talked about regions in terms of how exposed these regions are to rising sea levels, because the whole country sits, within about 3 meters above mean sea level. You can see the actual power of the waves here that are breaking on these reefs, dissipating very, very quickly, and then you have very little waves actually on the shoreline. Just to give you some kind of scope, this kind of breaking and dissipation of waves here, it's a lot smaller in width compared to, say, your regular beach if you went down to the Gold Coast or you went to the Sunshine Coast. Coral reefs are really, really effective at taking wave energy out very quickly, much faster and much better than anything we can build and any other ecosystem that we know of. I've selected 2 other sites which kind of show not just mid-Pacific atolls, but places in Tahiti. And this is Chopu, Tahiti. This is actually one of the places where we worked. It's relatively well known because it's a very famous surfing spot. But behind this reef here, there's also villages that are aligned on these reefs for coastal protection. And at the bottom here, we have Ningaloo Reef, which is a pretty classic fringing reef system, really large waves dissipating very quickly and really low energy coastlines. So the point here is that reefs are incredibly effective at taking out very large waves. and losing that ecosystem service, either through rising sea levels or a degradation of these reefs, potentially has some catastrophic effects in these regions. I wanted to show a YouTube clip here. I'm going to try this, Sean, because it's worth showing everybody what reefs can do in terms of breaking waves.
Yep, sounds good, Daniel.
Okay, sorry, I just stopped sharing just to avoid some of the issues.
Yeah, no, you're doing well, mate, managing.
You can imagine I'll be used to it now because I've been giving lectures to Zoom.
Very smooth, mate. Very smooth.
So you can see the YouTube clip here now?
We can.
All right, so this is, it was the site that I was just showing you before. This is what the waves look like there relatively frequently throughout the year. About 4 or 5 times throughout the year will look something like this. The wipeouts for entertainment, by the way. So this is I use this video a lot in my teaching just to keep people awake. So right where these waves are breaking is where the reef's actually growing and surviving. And I just use this as a bit of an idea. Not only that's one of the field sites in the talk where we collected wave data from, but that is an example of the kind of waves that will break on coral reefs and the role that coral reefs play in protecting these Pacific Island countries, for example. So this Fiji, Tahiti, Hawaii, any of these places are relying on coral reefs to do this job. Without it there, those waves will be impacting on the coast. Okay, so I won't do the second one. Needless to say, there's a bunch of those style of, bunch of those kind of videos in those environments. So let's get back to the talk. So that spot that I was just showing you there is Chopu, Tahiti in the top right-hand corner. About 200 meters behind that is a muddy environment with a village reliant on that reef for breaking those waves. So this is a kind of classic infographic to describe the role of coral reefs in reducing wave energy. The statistics that are usually thrown around, they're a bit kind of wishy-washy really, but about 97%, even up to 99% or almost all of it, of the wave energy is removed by these coral reefs and allows for the infrastructure to be built in these low-lying regions. Australia is no different. Most of the coast of Queensland is really low energy and it's reliant on the Great Barrier Reef, taking out most of the swell wave energy. We don't have very many surfing beaches north of Fraser Island, and that's because the Great Barrier Reef turns on and takes out all of the waves. So Australia is a country that's really reliant on coral reefs for protection as well. So just to get into the processes that actually remove this energy and how they might change in the future, there's really 2 main processes that we can get into and look at when we want to try and forecast change in the future. The first one is wave breaking, which is primarily governed by water depth, which makes sense. And you can predict almost the height of waves in any surf zone throughout the world if you know the water depth. The other one is friction or drag. And so this is governed by bed roughness. In beaches, you've got sand, they're not that rough. But in coral reefs, you have lots of complexity, lots of little nooks and crannies, mainly, which are really important for the ecology of the reefs and the recovery after events like bleaching. But they're also really important for the protection of coastlines because they remove energy through friction. It's the equivalent of like rubbing your hand over Teflon between rubbing it over sandpaper. Same kind of functions apply. It's just this time it's removing wave energy across the top of the reefs. So it's the interplay between these 2 processes that make them the most effective natural barrier to waves that we know of. However, these 2 things are going to change in 2 ways. So breaker dissipation is going to change when coral reefs fail to keep pace with sea level rise. So coral reefs can grow up to meet sea level, but it happens relatively slowly in environments like Chopu on the top right. It's a fairly extreme environment. It's going to take a while for it to start building and accreting vertically. And so if they don't keep pace with sea level rise, you expect a reduced amount of energy being lost due to wave breaking, like what we have on the top right there. The other thing is if you get a transition of reefs with something like what we have in the bottom right, you would expect there to be greater a reduction in the energy removed by coral reefs because of a degradation in the structural complexity. Within the models that I use, it's a roughness term. And so that's the rugosity is another term that we use. It's actually just fluid mechanics. You can do the same kind of stuff with forests. If you start, logging and removing forests, you can get changes in the wind patterns. Same kind of ideas apply here. So the conceptual idea of the kind of modeling we ended up doing, which I'll explain in a minute, is kind of described what we have on the right here. On the bottom left-hand corner is a reef that's actually kind of in its worst case scenario. You've had a rise in sea level. There's been erosion and loss of structural complexity of the reef because it's degraded due to things like bleaching and any other kind of stresses that have impacted the reef. And then on the top right-hand corner is the best case scenario. You've got a reef that's very vibrant and healthy, maintains or even grows its structural complexity and keeps pace with sea level rise. So you more or less have very similar wave conditions to what you have at present in the future, even with rising sea levels. So that's the kind of two spectrums of the best potential responses of a coral reef to a rise in sea level. Okay, so this is getting down to how we actually parameterize the reef when we wanted to actually investigate changes on the reef into the future. On the top here is a couple of photos. On the top left is a photo from Palmyra Atoll. It's considered a relatively, it's a reef that hasn't had as much human impact, at least local human impact. Of course, global impact due to things like temperature increase and bleaching can affect any coral reef, but it's really structural complex. Lots of sharks is the other aspect of this reef. Very high score of this roughness coefficient in terms of the hydrodynamic models that have been run across these reefs. The two photos on the right here are the ones that we had a look at in French Polynesia. They were actually recovering after a cyclone and crown of thorns event. So they were still pretty complex, but they were still kind of recovering. You can see that we get reduced kind of scores on these reefs as you reduce the complexity. And this photo here is actually, that's the pressure transducer that I still use today. We have a bunch in UQ now. And basically what I do in terms of the field is jump through the surf zone and cable tie these pressure transducers to the reef to measure the waves to make sure I get accurate readings or accurate modeling. There was a bit of reduced OH&S in French Polynesia that allowed us to do that. I don't know how UQ would go. Swimming off the edge of a reef, but yeah, so I don't think I could do that now. I'd have to think of something different, but that's more or less what we were doing in French Polynesia. And just to link the kind of observed changes in structure here, this is linking it again to the kind of forecasted changes, potential changes of coral reefs into the future under climate change. So I'll just get on to what we did. So went to 4 different sites in Tahiti and French Polynesia. The idea of these 4 different sites is they are different wave exposures and different types of reefs, so at least they look different. So you could get at least a range of different reef environments, even though you're kind of in the same location in the world. So we had 3 sites in Moorea, and we had 1 site at Chopu, Tahiti, which was that site I showed previously. The dominant wave energy is from kind of this direction from the southwest, so we get a nice set of reefs with different wave exposure, really exposed down on these environments in Chopu and Hapiti, and then different exposure in Tiahura and Tamai. I won't go through this in too much details. This is here actually for more of the hydrodynamic people, and I don't know how many people are in the audience who do this, but on the left here is just showing the sites where we went and some of the records that the location of the wave gauges that we use that I showed in a previous slide. But on the right here is actually, once we run our wave dissipation model across these reefs, how accurate we can get it when we have data to train off. So the incredibly accurate models, this is the comparison between the measured and modeled wave climate in the lagoons in, which side is it? It's in Tiahura on the top here. You can see how closely our modeled red curve tracks with the measured curve. And this is the benefit of actually going into the field and doing this is I've got really high confidence in our calibrated wave models that we ended up putting together in these sites. You couldn't really do this as well if you didn't go into the field and collect some data. And that's a point I had to make in this paper because this kind of data set is not all that common. So what did we do to try and look at the potential change in wave conditions in the future in these sites? So went and calibrated the wave model. So field measurement combined with a process-based wave model. Then ran this through a bunch of Monte Carlo simulations with 3 primary inputs. So this was to try and deal with the potential range of futures of sea level, structural complexity. How is the reef going to respond to an increase in sea level? Is it going to grow up to meet it, or is it going to degrade and erode? So we have a range of inputs. We ran the model in total, I think, about 250,000 times for each of the different scenarios, but for each individual one, it was 40,000 times. The 3 different kind of values that we varied within our model was sea level rise, which leads to a decline in breaker dissipation. We then changed structural complexity, which leads to a decline in frictional dissipation, and then how the reef was going to respond to sea level rise, which again reduces this breaker dissipation. And as I mentioned before, it's the interplay between those 2 dissipation functions that will change wave climate in the future on coral reefs. Okay, from that, we run this back into our calibrated model, or the same model that we used that was calibrated before based on the measured field conditions, and then come up with a value that is adimensional, but it's basically a scaling factor that tells you how much wave climate has increased near the shorelines in the future. So if you have a value of 2, it's 2 times larger than it was at present. We also had, for the sake of kind of plotting and graphically kind of visualizing the data, combined structural complexity and the reef response into this reef health index. The idea there is that if you have a reef that's really nice and rugose and it also can respond to sea level rise quickly, it's probably going to be a pretty healthy reef. So that was kind of the idea. The actual results I'm about to show you were surprising. I hadn't really, I'd mostly been somebody who focused on just coastal processes, and it's a bit more of a narrower field, but as soon as we started looking at this, some of the results led to some interesting insights that led it to kind of having a bit more impact. So we went through a number of different scenarios once we had all this set up. So it was looking at this degraded reef at present sea level, a worst case scenario, most likely future and present conditions. So the degraded scenario was, we kept at present sea level, but we just wanted to see what would happen if we had a reef that lost all of its structural complexity and formed mostly something like a breakwater, like you'd see out on any beach where breakwaters are used, and a little bit of erosion on the reef, which is more or less equivalent to a loss of those actual individual corals. So about 20 centimeters of erosion. A worst case scenario is just increasing sea level on top of a reef that's no longer functioning. It's like increasing sea level over the top of a breakwater. So that's what we considered. It's pretty extreme, that instance. There'd still be some roughness on those reefs even in the future, but this was just kind of the worst case scenario. And then we looked at the most likely future, where we looked at the range of sea level rise predictions from the IPCC. It's pretty similar to the modal global sea level rise prediction at Tahiti. Looked at a range of structural complexity values, which were kind of within the range of what's been observed previously in coral reefs, and also used the maximum rate that's been observed of accretion on the reef in terms of shallow water reef accretion, which is, it doesn't quite keep pace of with sea level rise. This is something we had to include based on some of the reviewer comments that a reef, even if in its best kind of accretionary phase, doesn't necessarily keep pace with our forecasted rise in sea level. So the first result was this one. I'll just explain it kind of quickly. So this is our most likely scenario. So our full model runs. What I have on the right here on the x-axis is sea level rise in the top left. This is this reef health index score, so how healthy the reef is. And this is a normalized wave climate. So this is so we could compare between all the sites. And the main result here is that it's not actually sea level rise, but it's the health of the reef, which is the main determinant of the future wave climate on coral reefs. Based on our parameterization, this makes sense, but most of the time, in a lot of the ways in which we look at ecosystem services on coral reefs, it's usually just running sea level rise over the top of a reef at present, and then you look at what change in wave climate you see, but the health of the reef was a much bigger driver. So they can kind of govern their own wave climate. You'll still get the impacts of sea level rise on the coast, but at least you don't get this increase of waves if you've got a really healthy reef. And this was actually to the point that we could kind of almost predict what wave climate was going to look like if you could kind of figure out how the structural complexity on your reef was going to change, or the response to your reef was going to change. So what was it going to do in the future based off those two scores? You could have an idea of what the wave climate was going to be like. Just a point, that's very hard to do, forecasting what the reef's going to look like in the future, but that was a kind of interesting result that we found from this kind of modeling exercise. The next results were actually even more, like, using the term interesting, but it was quite surprising. So what I'm going to show you here is a typical kind of probability curves. You can just focus on the 50% probability in this dotted line here. Now, on the bottom here is the potential increase in wave height. So if you get a value of 2 times larger, 3 times larger. And we have the different colors associated with the different scenarios that I've discussed previously. And what we have is our kind of most likely scenario in the future. You're probably going to get a wave height increase of about 2 times greater than present. While that's quite bad, in some of those reefs, that sounds quite bad. In some of those reefs, that's actually a relatively small increase in wave height. So it's only something like about from 20 centimeters to 40 centimeters. Although it probably does suggest that during things like cyclones, this would be a lot worse than what we would have at present. But we weren't modeling cyclones here. It's something just to consider as well. The real interesting result, though, was the next one. That blue result there includes sea level rise. This one doesn't. This red value here, this degraded reef scenario, this is just if the reef lost its structural complexity, eroded a little bit, but only about 20 centimeters, only about the size of some of the coral colonies on the reef flats. You got an increase of wave height that was greater than what we were predicting by the end of the century. So that was a surprising result, and I ran this many, many times. The paper actually took a lot longer to get out to make sure this was realistic, based on our kind of parameterization, and it more or less was. And then if we rise sea level on top of this degraded reef scenario, we get a very large increase in waves, so 6 times larger. Again, these scenarios are pretty pessimistic, but it gives you the idea of the kind of endpoints on the spectrum of where you might get if you get this widespread degradation of coral reefs. The other point that was kind of came out of this is that if you can maintain some form of structural complexity on your reef systems in the future, it seems to do increasingly more work for you. So the change in present sea level conditions of a degraded reef is about 2 times difference in the wave height. The point that's getting made here is that the difference between rising sea level on a reef that still maintains some of its structure, which is the blue value here, and a reef that's lost all of its structure, which is the magenta value here, there's a very large change in potential future wave heights by the end of the century. And this is even a reef that isn't even quite as healthy as what we have at present. So the idea here, I thought this was quite a good result, is that even reefs that aren't functioning as vibrantly as we're used to seeing them will still do a lot of work for you in the future in protecting the coastlines, rather than something that's acting more or less like a breakwater. Okay, so let's just put this into 3 different kind of perspectives. The first one is the health of coral reefs is the main determinant on future wave climate on tropical coasts. You'll still get the impact of sea level rise, so that's important to consider. So you get erosion due to sea level rise, but you don't necessarily get the threat of greater waves if your reefs are healthy. Reefs that maintain some of their structural complexities can still provide some important protection in the future. The real negative aspect, which is, I had to give a couple of interviews on this, and there was only a couple of news outlets that didn't actually focus on this very specific point. It was new to the whole communication thing. I'm sure there's a lot of people here who are listening to this who are a lot better at it, but this was the thing that caught people's attention, was that if you have a few catastrophic events that maybe degrade reefs down to something that's like a breakwater, it won't take to the end of the century where you get a dramatic increase in wave height. It can happen very quickly. So it could happen over, I can't give you a timeline on it, but it can happen after a devastating event on a coral reef that leads to a loss of that structural complexity and erosion. But even in the future with some of these reefs that might end up degraded, there's still an immense coastal protection value associated with them. So that's something to focus on, is that if you can manage the reefs into the future in some way, they're going to be doing a lot of work for you. even if they're not quite the same as they've been previously. Now, I was going to link just very quickly into what this actually means on the coastline, and I'll just do this quite quickly. This is what I wanted to try and discuss maybe later on if people are interested, but it is what this actually means for low-lying reef islands and tropical coastal regions. So in the interest of kind of making sure I don't go over too much, I might just flip to those slides. So there's two kind of approaches of how we then forecast what this means for the habitability of the coast. And one of them is assuming these islands kind of remain static and seeing how the inundation increases due to this increase in wave climate. And one of the increase in wave heights, and one of the biggest studies on this is a few years ago, which looked at some of the atolled islands. And what we have on the right here is a few different sea level scenarios, but the timeline when you start getting return periods of very frequent inundation. And the problems here that they were looking at was whether or not you'd be able to maintain your freshwater lenses on the islands. So even if it is somewhat habitable, if you don't get fresh water, or if you start getting frequent inundation on the islands due to this increase in wave climate, you are going to have islands that are not as habitable much quicker than just if they start, say, drowning in kind of quotation marks. However, one of the criticisms of this is that it's assuming that these islands are static, they're made of sand, and these islands can respond. And so what I'm currently working on, which is trying to link to the research I just presented, is something that's a little bit more like what we see here. On the right here is just a profile transit through one of these reef islands and what happens to this island from this kind of dotted line to the solid line, what happens to this island when you increase sea level on it. So this was some physical modeling and also some numerical modeling. But one of the main points here is that islands don't just drown, they actually accrete vertically. If they're allowed to erode their shorelines and actually put sediment on top of the island, they'll still survive under rising sea levels and even increases in wave climate potentially, if you can somehow maintain the sediment budgets on these islands, and they can accrete vertically and still maintain some habitable areas. One of the problems with that, though, is that there's lots of, say, inundation that occurs in order for that to happen. So sediment needs to be taken from the beaches, placed on top of these islands, and they need to move vertically. I've got this point here, which is a discussion for another time, but this is actually starting to take hold in some areas of coastal science. So this is coastal geomorphology. Coastal erosion is commonly seen as a really negative thing you want to avoid. There's one specific kind of seminal research who's trying to push this idea that it's actually a really important service. Erosion liberates sand from the coastline and allows the coastlines to build up vertically in response to sea level. The main problem with coastal erosion is not the actual erosion itself, it's if you have things built in the way of it. So it's one of those different kind of conceptual approaches that's probably worth considering, because erosion does liberate sediment and it does allow for the accretion of things like low-lying reef islands, and also places like tropical coastlines, like what we have in Queensland. I've got a really kind of low resolution, kind of almost direct outputs from the models that I'm actually trying to get out of the kind of wrapping and rerun again. But the point I want to make here is what I'm focusing on is not just the accretion of the islands now, but if you have a look at what's happening here, this is another cross-shore transect of an island. This is really low res, so I apologize. This would have been a little bit better if I had a bit more time. But what we're looking at here is that as you get sea level rise, rather than this big overwash and inundation of the island, what can occur is you get the buildup of the berm. It's like the buildup of a sand dune if you've been to the Gold Coast or the Sunshine Coast or wherever. That can build up due to sea level rise. And if you can protect that resource, to protect the sand on the island and build up that berm, you can limit the amount of inundation that can occur. You can stall the amount of erosion that can occur and overwashing these islands, and you can potentially push into the future the time it will take before these islands, low-lying reef islands or low-lying regions, become uninhabitable. Okay. So I make this point, and this is after talking to some people who actually live on Kiribati, and this is some of the work that we're doing now, is that there's been a focus on things like hard engineering by putting things like sandbags or seawalls in on these reef islands. Perhaps even some a focus on managing the reefs, which is really important. But one of the things that I would like more people to know of is how important the resource of the actual sand that's already sitting on the reef flat is. There's been a number of tragic approaches where seawalls have been put in that has exacerbated erosion on the islands, and you've lost sand off the reef flat. And that means that resource is gone and is very hard to recover. And so a future management approach that focuses on just maintaining the kind of the size of these kind of berms on these reef islands is really important. And you can kind of push further away this horizon where some of these entire countries may not be habitable. And I say this within the context. So Sean mentioned I've done a bunch of sea level work, and that is another aspect of what I do. The latest kind of modeling on sea level rise, we're not going to go for 1 meter. We're kind of baked into having 5 meters in the next, say, 500 years. If it goes badly, we're locked into 20 meters in the next 500 years. So there is a future of very high sea levels. And I know that's a long way away for us, but you know, that in the grand scheme of things, it's not a really, really long length of time. So a lot of the stuff that we're doing in managing coastal environments now is more or less a stall until you can kind of work out how you're going to deal with those much higher sea levels in the coming centuries. I'll leave it there. So the take-home points is that the future wave climate on the tropical coast is likely to increase, exacerbates this erosion, but coral reefs can control their own fate, and they're still going to be really important no matter really what happens to them over the next decades. They're going to have a really important service to play on tropical regions. But the stuff that I'm really kind of transitioning to now is how we can kind of understand what the likely response of these tropical regions are going to be, and how we can thoughtfully plan to try and protect the habitability of these environments. That's a relatively new area of research, so I'm more than happy to talk to people who have a bit more experience of doing this kind of work and communicating with people. I'll leave it there. So thanks very much for listening. And if you have any questions, you can answer them now or ask them now, or I'm more than happy to respond to anything via emails as well. So thank you very much.